Okay, so today I want to do a quick review on curved arrows. And I think for students in organic chemistry, curved arrows can be kind of confusing and almost seem irrelevant. Like, why do we have to put these here if we've memorized the reaction? Sorry, I had to take a drink. But for organic chemists, curved arrows aren't something that we've memorized the reaction and we're just going to use them to decorate the reaction, kind of. We use curved arrows to try to predict what the reaction mechanism is going to be. So especially as you move into organic chemistry too, it really helps if you can use arrows to do the same thing. So the big thing with curved arrows is you're going to see them in resonance structures and you're going to see them in reaction mechanisms. And there's a few rules about curved arrows. One is that they always start from area with extra electrons or excess electrons that can be shared. And two is they're never going to start, for one, they'll never start from a negative area. Sorry, I said that wrong. For number one, they're always going to start from a more negative area or an area with higher electron density. They will never start from a positive. And an example I always give is if you saw someone with a really positive attitude, they're not going to just come at you and attack you, right? But people who have more negative attitudes are going to be people who do the attacking. Like someone angry will be who comes at you. So the the attack of electrons start from the area that's more negative. And then the second thing is they're always showing the movement of electrons. So the first example I'm going to give you is an example in resonance. Okay, so when I look at this, I know that there's going to be a resonance structure. We have to start with an area of more electron density, and there's two areas like that. These electrons are on the oxygen or in the double bond. Both of these have extra electrons. Now, if these electrons moved down here, so what this arrow is showing, if these two electrons moved and formed a bond right there, your product would look like this. That positive charge would come from formal, this negative charge would come from formal charge as well. So if this is what you're getting, there's a big mistake here that there's 5 bonds to carbon. That would never work. So this isn't a possibility for the movement of these electrons. And that's more about Lewis structure rules. But a different possibility would be the double bond. That's another area with higher electron density. So if you show that, this bond right here moved up to become a lone pair on top. That negative comes from formal charge, and then this would be positive as well. And actually, these are resonance structures. So in reality, you have a partially positive carbon and a partially negative oxygen anytime you see a carbonyl or a ketone. So what we saw was these two electrons moved to become a lone pair up on top. So that is seeing where a bond breaks. Sometimes you'll see bonds form. That's what we did here. A bond would have formed here if there hadn't already been 4 bonds to this carbon right there. Now another example of a bond breaking or forming would be in benzene. Well, I guess not technically benzene. If you have this lone pair right here, this lone pair can come down and form a bond right here. But if it does so, that right there would have 5 bonds to carbon. So this bond breaks, and you end up with a lone pair right here and your bond here. So that's another resonance structure where we saw movement of electrons between 2 spaces. Another way that I've seen this drawn, not usually by organic chemists, but more by biochemists, is if bonds are made up of lone pairs. So see, this bond right here is made up of 2 electrons. This bond right here is made up of 2 electrons. And then we have our lone pair that's negatively charged. So these electrons come here to form a bond, and then this lone pair that was making up a bond moves over to just be on the carbon. So it would look like this. So your negative charge is now down there. So this somewhat denotes the same thing as this, but in an organic chemistry class, that's not really going to be relevant as much. Sorry, I got quickly interrupted, but that really wraps up the resonance section or the watching electrons move. It's either bonds forming or bonds breaking. It's like an arrow. The arrows keep track of where the bonds has formed and broken. But where you're going to see it a lot more is going to be in actual reaction mechanisms. So even if you're not incredibly familiar with curved arrows, hopefully if I draw, this lone pair is going to attack this proton, you'll know that this lone pair forms a bond with that proton. So one of the lone pairs formed a bond, and then we have our 2 other lone pairs on top. Water is actually bent, but I didn't worry about drawing that structure. So what used to be this lone pair right there is now shared between this hydrogen and this oxygen, forming a bond. So that bond is just made up of those 2 electrons. So hopefully that's helpful for you. One that you're going to see a lot if you're in OChem 2 is something negative. So I'll just write like OH minus. We'll do that one again. And oftentimes, if you have a carbonyl carbon, like I showed earlier, there's a partial positive on this carbon right here, and this is partially negative due to the resonance structure. So this will come in and attack, and this bond will break, and the lone pairs that were formerly in this bond will go up to the top. So these will form a bond between this carbon right here and the alcohol. So that's the first thing we draw. And then this used to be a double bond, but that broke. There used to be a double bond there, but it broke and came up on top. So something that sometimes helps is if I draw it with color, so you can kind of see. So actually, I'll do this. So the electrons that are moving will be drawn in color. And I'll do a third color. Oh, getting my markers all mixed up. I'll do this color. So it's kind of light. Can you even see it? No, I'll do blue. Okay. So these blue electrons right down here will be attacking here and forming a bond, and then this bond is going to break and add to the other lone pairs that are up on top that I didn't draw. So what you end up with, this bond doesn't move, this bond doesn't move, this oxygen doesn't move, and then a bond here between this alcohol and hydrogen. So what used to be these electrons now made this bond right here. And then this bond broke. You got 2 electrons that came up top. So that's just following the movement of electrons in reaction mechanisms. And so whenever I look at a practice problem, like if I ever have like an H plus and anything negative, I don't just have this memorized. Like I don't just automatically know what's going to happen. I look at where there's more electron density. So like right here, this double bond or this lone pair is extra electrons with a triple bond. So I'm assuming this is going to attack something positive, and there's only one positive thing it can attack. So that must mean a bond is going to form between this carbon and this hydrogen. And that's why I draw the arrow attacking there. Another one is if you have like a substitution reaction. That's something that we did a lot in chapters 6 and 7. So if you have this, you know this is a polar bond. So this is partially positive on the carbon right here, right? So this negative thing, looking for a partial positive, it finds one, it attacks there. That must happen. But then there will be 5 bonds to carbon because of the implied hydrogen, so then we know that bond is going to break. So what we're doing is showing that these electrons form a bond between this carbon and that carbon, and then these electrons must break. So these 2 electrons are still there, but they're just shared equally now between this carbon. And then these 2 electrons have gone to be with a bromine. So that's how we get that reaction. So I'm just showing sort of the way I look at electrons and moving and why I use curved arrows. And remember, it always starts from the negative position and it moves towards the positive to help you predict how reactions are going to unfold. So I hope that was helpful for you. And if you have any questions, please just let me know.